talk about how the launch angle affects our motion. So when I talk about the launch angle, I'm talking about the angle that the ball is released. So I'm talking about the angle between the direction of the initial velocity of the ball and the horizontal. The thing that's the same in these videos is the initial speed of the ball, not the velocity, because if I'm launching it at different angles, the speed is going to be pointed in a different direction, which means we have a different velocity, but the speeds are going to be the same. I'm going to give the ball the same initial speed, but in different directions. Okay, so I got the ball in the hoop. Now, let's see what happens if I change my launch angle. Let's increase my launch angle. Okay, so we can clearly see that the launch angle that I launched the ball at definitely affects the motion of the ball. The launch angle affected the ball's horizontal displacement, and it also affected the ball's vertical displacement. For all three videos, the ball had the same starting height, each ball had the same starting speed, each ball had the same initial horizontal position. It was the same distance away from the net horizontally. The only thing that was different was the launch angle. Remember, when talking about 2D stuff, we want to talk about X stuff and Y stuff separately, or horizontal and vertical stuff separately. Let's first talk about how the launch angle affected the maximum height of the ball, or its peak height, its maximum vertical displacement. The ball in the third video had the highest launch angle, and the ball in the first video had the lowest or the smallest launch angle. You can see the ball with the largest launch angle went up the highest. It had the biggest maximum height, and the ball with the smallest launch angle had the smallest maximum height. From this you can get that the higher the launch angle, the higher the maximum height of the ball. Now let's talk about why that is. So if I draw vectors for the initial velocity, right, represented by the blue arrow, the length of all three of the blue arrows is going to be the same because the ball had the same speed in each of the videos. The difference was the direction of the initial speed. Okay, so I have broken down the initial velocity into its horizontal and vertical components for each of the three videos. This is video 1, 2, and 3. Let's talk about just the vertical components right now. So you can see the smaller the launch angle, the smaller the vertical component of the speed. So as the launch angle is increasing, the vertical component of the speed gets bigger, which means when the launch angle increases, more of the speed is pointed in the vertical direction. The more vertical speed you have, the higher the ball is going to go vertically. So as the launch angle gets bigger, the vertical component of the speed gets bigger, which means the ball is moving faster in the vertical direction, which will allow it to get up to a higher height before gravity can slow it down and turn it around. So you can see this very clear relationship. The bigger the launch angle, the bigger the vertical component of the speed, the higher the ball is going to go. Alright, now what about X stuff? Did the launch angle affect how far the ball went? Well, here's x3, x1, and x2, or the horizontal displacement of the ball. In the video, the basketball pole was in the way, so they often bounced back, but if there was no pole in the way, then the ball would keep following its parabolic path, its curved path. The ball with the medium launch angle went the farthest horizontally, and the ball with the large launch angle and the small launch angle didn't go as far horizontally as the ball with the middle launch angle. I'm going to go back to my speed triangles over here. We can see that as the launch angle increases, the vertical component of the speed gets bigger, which means that the horizontal component gets smaller. So for the smallest launch angle, the horizontal component of the speed is the biggest. The ball with the lowest launch angle, most of the speed is pointed in the horizontal direction. On the contrary, when I had a big launch angle, the ball went very high, had a very large vertical displacement, but it didn't go as far horizontally because most of the speed was pointed in the vertical direction. there was a very small component of the speed in the horizontal direction, which is why the ball went mostly vertical and didn't go very far horizontally. So intuitively, you might think that this one would go the farthest, the one with the lowest launch angle. Well, that's not necessarily the case. The one with the middle launch angle actually ends up going the farthest horizontally. And I don't want to get too much into it right now, but it has to do with how long the ball spends in the air. But what you can say for sure is that the larger the launch angle, the smaller the horizontal component of the velocity is going to be. As long as they're all going the same speed, which they are. They're all going the same speed, just at different angles. So let's see how the initial speed that the ball has affects its motion. So what does that mean? So in the first video, I'm going to throw it with a little bit of force, which will give it a slow speed. In the next video, I'm going to throw it with some more force, which will give it a little bit more speed. It'll be going at a decent speed at the beginning. And then I'm going to launch the ball with a lot of force, which is going to give the ball a really fast speed. So the ball's going to be moving fast. Okay, the launch angle is the same for the ball in all three videos. The initial horizontal position is the same. The initial vertical position is the same. The ball always starts from the same height. The difference is the starting speed, or the initial speed of each ball, is different. In the first video, the ball had a small initial speed, and in the last video, the ball had the greatest initial speed. So over here, I have the vectors drawn for each of the initial velocities. The initial speed in the first video is smaller than the second video, which is smaller than the third video. Which means that for the first video, I have the shortest arrow, and in the last video, I have the longest arrow. All three initial speeds were pointed in the same direction, so these are all at the same angle. So again, I'm going to break these down into their components. So I broke the velocities down into their horizontal and vertical components, and so you can see that as the initial speed, v0, gets bigger, the horizontal and vertical components also get bigger, right? Because if there is more total speed, the horizontal and vertical components are going to be bigger. So if the whole thing gets bigger, then the components are going to get bigger. Let's talk about the vertical displacement first. Well, when the initial speed was bigger, the vertical component of that speed was bigger, and so the maximum vertical displacement, the maximum height, was also bigger. The bigger the vertical component of the initial speed, the higher the ball is going to go. What's key here is that the maximum height depends on the vertical component of the initial speed, not the total speed, but the vertical component is what determines how high the ball goes. We don't care about the horizontal component because the horizontal speed has nothing to do with the vertical displacement of the ball. Remember, we don't mix horizontal and vertical stuff together. We talk about them separately. The same goes horizontally. As the speed got bigger, the horizontal component of the speed also got bigger, which means that the ball is going to go farther horizontally. It's going to cover a bigger horizontal distance if it has a bigger x component of the speed. So from all this, because all of these are pointed at the same angle, the ball with the greatest initial speed has the greatest horizontal and vertical components of speed, which means it is going to have the biggest horizontal and vertical displacements. Okay, finally let's talk about the starting height of the ball. So in all these videos, I'm going to give it the same launch angle. I'm going to launch the ball at the same angle every time. Give it the same initial speed and start the same horizontal distance away from the hoop. So I'm starting at the free throw line every time. But I'm going to change the starting height of the ball, the initial vertical position of the ball each time. Let's see how that affects things. So for the first video, I am going to squat down. So the ball is going to start a lot lower. than in all the videos you've seen. So now I'm going to jump higher and let go of the ball when I'm at the top of my jump, so it's going to have a higher starting height than it has been. Alright, this is the height of the video. I highly recommend that you pay attention to this information about starting height. In all of these videos, the ball has the same initial speed, the same launch angle, starts at the same horizontal position, x0. The difference is the starting height. Each ball starts at a different height. And so clearly that affected the path of the ball. The starting height of the ball in the third video is the biggest, and in the first video the starting height is the smallest. So let's talk about how that affects the maximum vertical height first. As the starting height increased, so did the maximum vertical displacement. So my y=0 reference line is the ground, right? The ground is 0. And as the starting height increased, so did the maximum vertical displacement, the peak height. So the higher the ball starts, the higher it is going to go vertically. So the ball that started the highest went the highest, and the ball that started the lowest went the lowest. Okay, what about the horizontal displacement? So if the ball had kept going and not hit the pole or anything, and hit the ground, the lower that the ball started, the less horizontal distance it covered. The ball that started the lowest went the shortest horizontal distance, and the ball that started the highest went the greatest horizontal distance, and the ball that started the highest had the greatest horizontal displacement. Why? Because the ball that starts the highest is going to spend the most time in the air. The more time the ball is in the air, the longer it has to travel horizontally. As the ball's flying through the air, there's nothing to change the horizontal motion. So if the ball is in the air for a longer amount of time, it's going to keep traveling with its horizontal speed for a longer time and thus cover a larger horizontal distance. So all three of these balls have the same horizontal component of the speed. They're moving horizontally at the same speed because they start with the same speed. But because this ball starts the highest, it's going to be in the air the longest because it goes higher. So it's going to be able to cover a greater horizontal distance. I keep writing like I'm running out of time because I am running out of time. In order to do this in a timely manner, I'm splitting this up into 3 videos. So don't worry if the time part didn't make sense. Part 3 is going to be all about what affects the time that the ball spins in the air. So watch part 3. So as you can see, making your free throws is totally a projectile motion game. So if you're really good at free throws, then you should be good at projectile motion, and vice versa. If you are really good at projectile motion, you can learn basketball, which is what I'm trying to do. Maybe that's easier said than done.